There is a phrase that once deeply unsettled the greatest physicist of the 20th century: spooky action at a distance. That was how Albert Einstein described quantum entanglement, a phenomenon so strange it seemed to violate the very structure of reality. Two particles, separated by vast distances, somehow remaining instantly connected. Change one, and the other responds immediately. No signal, no delay, no visible connection. For decades, this seemed like a glitch in physics, an incomplete theory waiting to be fixed. But what if entanglement isn't a bug? What if it's the blueprint? Today, physicists are exploring a radical idea: that quantum entanglement is not just a strange side effect of quantum mechanics. It may be the geometric foundation of spacetime itself. To understand this, we need to start with what entanglement really is. When two particles interact at the quantum level, their properties can become correlated in a way that classical physics cannot explain. Their states become linked. Measure one particle's spin, and you instantly know the spin of the other, even if it's on the other side of the galaxy. Experiments have repeatedly confirmed this. Entanglement is not theoretical. It's measurable. It's real. And crucially, it does not allow faster-than-light communication. No usable information travels instantly, yet the correlation is immediate. This is where geometry enters the picture. For centuries, physics assumed that space is fundamental. Objects exist within space. Distance separates them. Geometry defines relationships. But quantum theory suggests something more radical. Maybe space itself emerges from deeper relationships. In classical geometry, distance is defined by spatial separation. In quantum theory, relationships are defined by entanglement. And here's the surprising part. Entangled particles behave mathematically as if they are closer than space suggests. Not spatially close, but informationally close. In recent decades, physicists working in quantum gravity and string theory began noticing something remarkable. The mathematics describing entanglement patterns looks strikingly similar to the mathematics describing curved spacetime. In particular, work related to the holographic principle suggests that the geometry of spacetime may emerge from quantum entanglement. The holographic principle proposes that the information describing a volume of space can be encoded on its boundary, like a hologram. In certain models, the strength of entanglement between quantum systems directly determines the curvature of spacetime. In simple terms, change the entanglement structure, and you change the geometry. This leads to a profound idea. What if spacetime is not fundamental? What if space is stitched together by entanglement? Imagine spacetime not as a smooth fabric, but as a network, a web of quantum connections. Each connection represents entangled relationships. Where entanglement is strong, spacetime is tightly connected. Where entanglement weakens, space stretches. In some theoretical models, if entanglement between regions drops to zero, spacetime literally tears apart. Geometry, then, is not primary. It is emergent. This flips our intuition upside down. We normally think that particles are connected because they are near each other in space. But quantum gravity suggests they might be near each other in space because they are connected by entanglement. Distance may not create connection. Connection may create distance. This perspective has gained traction through research in areas like ADS/CFT correspondence, a duality discovered in string theory. In these models, gravitational physics in a higher dimensional space can be described by a quantum field theory without gravity on a lower dimensional boundary. And the bridge between them? Entanglement structure. Even more intriguingly, certain geometric objects known as wormholes appear mathematically equivalent to specific entangled quantum states. This idea is summarized by a bold conjecture: ER equals EPR. ER refers to Einstein-Rosen bridges, wormholes. EPR refers to the Einstein-Podolsky-Rosen paradox, entanglement. The proposal suggests that entangled particles may be connected by microscopic wormholes, not traversable tunnels for travel, but geometric connections in spacetime itself. If true, entanglement is geometry. This doesn't mean we can use entanglement to teleport ourselves across the universe, but it suggests something deeper. The universe may be built from relationships rather than objects. Instead of particles sitting in space, space may arise from particle relationships. This shift matters because one of the biggest unsolved problems in physics is unifying quantum mechanics and general relativity. Quantum mechanics governs the very small. General relativity governs gravity and the structure of spacetime. They are both incredibly successful and fundamentally incompatible. But if spacetime emerges from quantum entanglement, then gravity itself might be a large-scale consequence of microscopic quantum relationships. In that case, the conflict between the two theories dissolves. They become different descriptions of the same underlying structure. The geometry of entanglement could be the missing link, the code beneath the universe's operating system. And this leads to philosophical implications. If space emerges from entanglement, then separateness may be less fundamental than connection. What appears distant may be deeply unified at a deeper level of reality. The universe may not be built from isolated pieces, but from patterns of correlation. Reality, at its core, may be relational. We are used to thinking in terms of objects and locations. But quantum theory increasingly suggests that relationships are primary. Geometry may not be the stage upon which physics unfolds. It may be the shadow cast by deeper quantum information. We are still far from a complete theory of quantum gravity. Many of these ideas remain theoretical, supported by mathematical consistency rather than direct experiment. But the trajectory is clear. Entanglement is no longer viewed as a strange anomaly. It is becoming central. The more we study it, the more it looks like the scaffolding of reality itself. Einstein called it spooky action at a distance. Today, physicists are beginning to suspect it is not spooky at all. It is structure. The universe may not be made of things. It may be made of connections. And geometry, the shape of space and time, may simply be the visible imprint of invisible quantum relationships. If that is true, then unlocking entanglement is not just about understanding particles. It is about decoding the architecture of existence.